You've done this already. You have a formula. It's up on the formula chart. It's the second or third from the bottom on the 7th grade chart. It says direct variation. It's y equals kx. You've seen k before. We've used it for a while. Does anybody remember what k stands for?
X over Y?
Flip it.
Y over X?
Yes. So we found k by doing y divided by x. And we've called it many things. Anybody remember the many names that this thing has had? Constant of proportionality.
I can't believe that looked.
Constant of proportionality. What else do we call it? Slope. Anything else? What did we do yesterday or Tuesday?
I have no idea.
Unit rate.
Unit rate. Any others? Might look at the word wall, see if any of those would fit. What did we multiply by?
Constant rate of
Constant rate of change. Constant rate of change. All right. I think that might be it. Anybody think of any others?
No.
All this is the same thing. We just do it over and over and over. It's called something different every time, but it's the same thing. Now we're going to add one more word to this list. Constant of direct variation. So you've got this constant of constant rate of change, constant of proportionality. Now it's going to be constant of direct variation. Constant of direct variation. If you think about what direct, this varies directly with this. It's a multiply relationship. That's what this means. It's a multiply relationship. Anytime you can take your x and multiply it to get y, it fits this category. It's a proportional relationship. It's a direct variation. This is the unit rate. It's a constant rate of change over and over and over. All of those things are the same. Okay? So with this, it is a proportionate relationship. It is going to be proportionate. What does that mean your graph is going to look like? Straight line. And what point does it have to hit? The origin, which is 0, 0. In order for something to be proportionate, it has to be multiplying. So there's no adding or subtracting. No adding or subtracting with this relationship. It should just be multiplying. Now, quick side over here, just something to make sure we understand. 10 divided by 2 is 5. What can you multiply 10 by to get 5?
0.2.
I heard somebody say 0.5. Is there another option? Think about 0.5 in a different form. Yeah. But you don't multiply by 1/2. There it was, 1/2. So 10 times 1/2 is 5. So if you're getting a relationship where it looks like it's dividing, we still need to write it like this. So just think of what is it dividing by. Now let's see what we can do as a fraction. This right here, from this 2 to 1/2, it's not a coincidence that we're dividing by 2 here, so we multiply by 1/2. So 10 divided by 5 is what? What? 2. 10 divided by 5 is 2. So 10 times what is 2? If 2 became 1/2, 5 becomes 1/5. So this 5 so if you're getting a divide relationship, flip it and make it a multiply relationship. You're going to get a couple that are that way. All right. We're just going to do a quick example and go through just kind of a review of what we've done in the past to what's going to work with this. We're going to compare games and at-bats. Why? I don't know. I just liked this example. How many times you go to the plate? 20, 30, 50, 160. And then at-bats is 62, 93, 155, and 496. So the first thing you're going to have to decide, is it a direct variation?
Wait, really fast. Is this like a sports thing?
No. I mean, this example, sure, but I only picked it because it doesn't go in a nice, neat pattern. The actual lesson doesn't have anything to do with sports. Is it a direct variation? How would we test that theory? What would we have to do to figure that out? What does it mean if it is a direct variation?
Then it would be like constant.
It's constant. What are we doing to x to get y? Multiplying. So I need to figure out, can I multiply by the same number each time to get y?
No.
No. Because
Don't be so quick.
Yes.
So there's a reason I picked this example. Can I multiply by same number each time? So how would I check that? What's the opposite of multiply? Divide. So what you have to do, and it seems really tedious, and I'm sorry, but it is what it is. You need to divide each one. Divide each y by x. So I've got 62 divided by 20. 93 divided by 30. 155 divided by 50. And 496 divided by, ooh, I put that too close together, 160. All right. So we're dividing. How many times can 20 go into 60? 3? 3.1, because that's come out to 60. And then I've got a 2.0. And that would be 0.1. How many times can 30 go into 93? 3. And that's going to be 90. And you got a 3.1. Anybody seeing a pattern yet?
Yes.
How many times can 50 go into 155? 3, and it comes out to 150. Then you have 50.1, 160 into 496. Any guesses? 3.1. It is, I would check it, like even now I'm still going to work it out. It's 480, subtract, that's 6, 160 is my leftovers.
So did you only get that example out of the book?
Yeah, I don't make examples. I pick bad examples. Either they're too easy or they're too difficult. So this, because it comes out the same every time, it is constant. It is a direct variation. I can do 20 times 3.1 to get 62. 30 times 3.1 gives me 93. 50 times 3.1, and so on and so on. Okay, so check each one. Hopefully it's going to show a pattern pretty quick. The math shouldn't be too difficult because you should, like, if this is 3.1 and this is not coming out to 3.1, then you can stop. Like, you don't have to keep going. Once you hit one that doesn't work, you can stop. Okay, but you do have to check every single one, because if this one isn't 3.1, but this one is, and this one is, if this one broke the pattern, it's not a direct variation. Okay, and then my equation that I can write for this, yes, that too. Y equals, what am I multiplying by each time? 3.1x. And this is my k. This is k. These are my k's. So it's basically like a unit rate, constant of proportionality. It's all that.